Hello and welcome back. In this section, we will start our discussion of thermochemistry and Hess's law, which involves using the first law of thermodynamics and measurements of heat capacities and enthalpy changes for various elementary processes, standard processes, to obtain useful information. Now, I have to warn people, this section of the class may be a little bit boring, it's a little bit dull, it's a little bit dry, but it's relatively simple. It's one of the simpler, more straightforward parts of the subject. And and the fact that it's a little dry and a little dull and yes, quite boring, should not be allowed to obscure the fact that it is useful, very useful in fact, in terms of allowing us to use one set of measurements to make predictions about or to infer information about processes for which direct measurements might be very difficult. So, that said, let's look at how this works. This is based on the fact that internal energy U and enthalpy H depend only on the state a system is in and are independent of history. So, if you take, for example, 1 gram of H2O at pressure of 1 atmosphere and a temperature of, let's say, 298 Kelvin, and I should say liquid water, then the enthalpy per mole, H subscript m for per mole, comma H2O liquid, all of this is in the subscript, at 1 atmosphere pressure, 298 Kelvin. It doesn't care whether we got to this water by condensing steam or by melting ice. In this condition, the liquid water has the same enthalpy regardless of what the past history or origin was. So, thermochemistry makes use of this feature of the enthalpy per mole, or the enthalpy and the internal energy, that these are functions of state. Okay. So, in thermochemistry, the way this subject works, or the way this area works is, we take advantage of either directly measured from experiment or tabulated, that we can obtain from tables of thermochemical data, tabulated values for 1. Delta H's, changes in enthalpy, for a collection of quote-unquote standard elementary basic processes or reactions. Think of these as words with which one can build sentences. So, delta H is for a whole collection of standard building block type processes or reactions obtained from either direct measurements or that have been directly measured and that are tabulated in appropriate tables. We have those data. And heat capacity, Cp, heat capacity under constant pressure, because remember, constant pressure conditions are much easier to realize experimentally. So, heat capacity data that are available to us are usually measured under fixed pressure conditions. So, we use heat capacity data together with measurements of delta H to ascertain estimates for delta H for processes or reactions that may be very difficult or impossible to realize or to measure directly. So, the number of chemical reactions is infinitely large, of possible chemical reactions or possible physicochemical processes, physical processes such as changes of state like melting or vaporization. There are an infinite number of possible physicochemical processes or reactions. It's not really possible or feasible to go and measure all of these independently directly, the delta H's for them. So, instead, we have one works with a tabulated set of delta H's for building block type processes and measurements of heat capacity for different substances per mole, and using those one can ascertain the delta H for other processes that may not, without having to measure them directly. It cuts down on the number of independent measurements one has to make and allows one to make predictions using tabulated data. So let's see, what is Hess's law? Hess's law. Now this law is simple enough that when you look at it, it is so simple, it's a little surprising it's actually given a name, but what it tells us is delta H for a composite process equals the sum over, say, subscript I of delta H sub I summation sum of delta H's for individual component subcomponent processes. Or in other words, if we have a reaction or a change of A going to B, this could be a chemical reaction, it could be a physical reaction, change of state, melting, vaporization, what have you. And for this we have delta H1, and then B going to C. For that, if the change in enthalpy is delta H subscript 2, adding these, we get A goes to C, and the total delta H is delta H1 plus delta H2. That's basically what Hess's law is all about. As simple as that. What changes is what these processes are, the nature of these processes, and how we tabulate data and use them in this context. So in this case, if we know delta H1 for this step and we know delta H2 for this step, we do not need to go and independently measure delta H for this reaction. We know right away that the delta H for this reaction is the sum of these delta H's, so we don't have to measure it independently. I should point out in this context that we are now on page 36 of the notes, and this business of Hess's law, this applies to all functions of state, not only to the delta H. It will apply later to delta G, change in Gibbs free energy, delta S, change in entropy as well. We will see that as we go along. But right now we are going to apply this largely to delta H, the change in enthalpy. Nomenclature. Yes, I did mention that this section of the subject is a little bit dry and a little bit boring, and I personally do not like getting too deeply bogged down in notation and symbols and nomenclature and jargon and things like that, but sometimes it is inescapable, unavoidable, and necessary, and this is one of those times where the jargon and symbols surrounding nomenclature and what different processes are called, unfortunately, regrettably, is inescapable, and we have to deal with it at least a little bit, but I will try to keep it as simple as possible, consistent with what we need to do and what we needed to do and what we need to understand. Okay. So there are various standard reactions and processes. Standard is within quotes. These are denoted by the superscript. Superscript is on top of within parentheses 0. So for example, e.g. for example, delta H, change in enthalpy, superscript within parentheses 0, tells us that that's the delta H for a process measured under so-called standard conditions, so that it is a so-called standard reaction. So how do we define a standard condition or standard reactions? We have to define the standard state. So the standard state of an element or a compound is defined as that element or compound in its pure condition. So there cannot be anything mixed in it. So for carbon, that would be the pure condition. So carbon, that's graphite. Why graphite? In its most stable form. So the standard state of an element or a compound is that element or compound in its pure condition, in its most stable form, because sometimes there can be multiple forms in which a compound or an element can exist. In its most stable form at a pressure of 1 atmosphere and a temperature of 25 degrees C. So 1 atmosphere pressure, 25 degrees C or 298 Kelvin temperature, standard pressure, standard temperature are defined like so, and the element or compound must exist in its pure condition in its most stable form. For carbon, at 1 atmosphere and 25 degrees C, the solid graphite phase is more stable than diamond. Yes, regardless of what one might think, diamond is thermodynamically unstable compared to graphite under standard conditions, 1 atmosphere, 25 degrees C. So the standard state for carbon is the solid graphite under this pressure and temperature. For water, H2O, at an atmosphere pressure and 25 degrees C temperature, the stable form is the liquid. So this is H2O in the liquid phase. That's an L within brackets, liquid, H2O, liquid phase at an atmosphere pressure, 25 degrees C, pure H2O. That's the standard state for water. Similarly for sulfur, similarly for other elements, and compounds, that's how we define the standard state. And that's denoted by this superscript 0. So the enthalpy per mole superscript 0 for H2O, this is H per mole of H2O, liquid, water in the liquid phase, pure liquid at pressure of 1 atmosphere, temperature of 298 Kelvin. Okay. Delta H, so that's H0. The change in enthalpy under standard conditions is the standard enthalpy, H superscript 0, in the final state with the final elements or compounds, minus the enthalpy in the initial state of the initial situation, also in its standard state. So for example, the delta H per mole of vaporization of water under standard conditions. That's a mouthful, I do know that. So let's look at this. Delta H, change in enthalpy, subscript per mole, comma, VAP, vaporization, per mole for vaporization, superscript 0, that tells us it's in the standard, under standard conditions for H2O. Let's look at what that means. Maybe the simplest way to go through this is to go through one example after another of what these terms mean and how they are used. So delta H per mole vaporization of water under standard conditions is the enthalpy per mole for water in the vapor phase at 298 Kelvin minus the enthalpy per mole of water in the liquid phase at 298 Kelvin. So this change in enthalpies is the delta H of vaporization, also known as the latent heat of vaporization. Similarly, we could write the same for latent heat of fusion. And here I should introduce this term, fusion, subscript FUS, I should write that more cleanly, FUS. This is synonymous to melting. This is just another way of saying a solid melting. So delta H per mole of fusion under the standard conditions would be H per mole for the liquid phase minus H per mole of the solid phase under standard conditions. Similarly, you can write delta H's of reactions. Delta H 0 for a reaction is the sum of the molar enthalpies, standard molar enthalpies of products minus the sum of the molar enthalpies of everything on the reactant side. So, for example, let's look at the reaction that could give us water under standard conditions. Let's look at the reaction that forms water from the elements. H2 gas plus 1/2 mole oxygen in the gas phase going to H2O liquid. Everything on the left-hand side starts out in pure states. So, pure hydrogen, pure oxygen, everything is at 1 atmosphere and 298 Kelvin. So, they are separated before, let's start with them separated. They react to give us liquid water. These are in their standard states. On the right hand side, we have 1 mole of H2O liquid, also pure, 1 atmosphere, 298 Kelvin. So, this is a chemical reaction, and given that everything on the left hand side and everything on the right hand side is in their standard state, we could say that the delta H for this process is simply delta H superscript 0, standard states on the left, standard states on the right, Rxn for this specific reaction, delta H for formation of 1 mole of H2O liquid in its standard state from the elements, in this case hydrogen and oxygen, in their standard states. That is called, this has a name, this is called the standard enthalpy of formation per mole of water. That's the delta H superscript 0 per mole for formation of H2O. That's the change in enthalpy for this reaction. And that's what it says here on page 38. So, page 38, analogues for chemical reactions, standard enthalpies of formation. Older language and older terminology was heats of formation or standard enthalpies of formation, denoted delta H superscript 0 for standard per mole for formation. That's the delta H0 for forming 1 mole of a compound from its elements where every participant is in its standard state. So, for example, for graphite, carbon solid, if we start with graphite as an example, plus oxygen in the gas phase going to CO2 in the gas phase. If we have standard states on the left and standard states on the right, the delta H for this reaction is delta H superscript 0 per mole for formation of CO2. How about for methane? Carbon solid plus 2 hydrogen gas, because in the standard state, remember, pressure is 1 atmosphere, temperature is 298 Kelvin. Under those conditions, the stable form for carbon is graphite, hydrogen is stable in the gas phase, that goes to CH4 in the gas phase. That would be delta H per mole formation for methane. Equations have to be balanced clearly, because this is also, and you can think of this as enthalpy, standard enthalpy per mole for methane minus the standard enthalpy per mole for carbon minus twice the enthalpy per mole of H2. Why the twice? Because there's 2 moles of hydrogen. And so on and so forth. Let's look at another example. Let's say I want to put glucose on the right. What's glucose? C6H12O6, and glucose under standard conditions is a solid, so solid. What's going to be on the left? 6 carbon, that's going to be graphite, plus we need 12 hydrogen atoms, so 6 hydrogen molecules, gas, 6 atoms of oxygen, so 3 oxygen goes to this. That is delta H per mole formation of glucose, and if everything is pure and separated here, pure and 1 atmosphere 25 degrees C here, and if this is also pure with nothing else getting mixed in, pressure of 1 atmosphere and 25 degrees C, that's delta H with a superscript of 0. You can think of this as enthalpy superscript 0 for standard state per mole of glucose, the absolute enthalpy, that's the enthalpy of this, minus 6 times the enthalpy per mole for carbon, minus 6 times the enthalpy per mole for hydrogen gas, minus 3 times the enthalpy per mole for oxygen gas. So these are the standard enthalpies of formation for compounds and how they are defined. These are tabulated, or there exist very large tabulations of standard enthalpies of formation for different molecules. Now you can see that the enthalpy change for a general reaction can be written by suitably combining delta H per mole for formation of the reactant and product species. And that's why it's very useful, because if we have a tabulation of the enthalpies for the formation reactions, standard enthalpy of formation delta H0, standard conditions for formation of 1 mole of the compound from its elements, where the compound and the elements are all in their standard states, 1 atmosphere pressure, 25 degrees C, pure states, most stable conditions. So that's these data are tabulated for a whole litany of compounds. Once we have those, we can use those to estimate the delta H for any reaction that those compounds participate in. Oh, by the way, what's the standard enthalpy change for formation for an element? Let's say we ask what's delta H per mole for formation for the element oxygen gas equals what? So that's for the reaction where on the right hand side we have oxygen gas. The only element is oxygen, so we are forming it from its elements. The only element is oxygen, but that's in its standard state is oxygen gas, 1 atmosphere, 298 Kelvin, 1 atmosphere, 298 Kelvin, 0. There is no reaction necessary. So what you will find is that delta H per mole for formation for elements, for pure elements, 0 for this reason, always 0. Because the reaction in which the element is going to be formed is, well, the element itself, and both left and right hand side are in their standard states. So the delta H of formation for elements is 0. Where we will go next is look at some examples of using the delta H's of formation for different compounds to reconstruct the delta H for a reaction. We will go through some of the algebra and some examples of how one actually calculates the delta H for a reaction given the delta H's of formation for the compounds that participate in that reaction. But to foreshadow that, I'll just quickly write out an example. If we have A moles of A plus little b moles of B reacting to give us little c moles of C, then the delta H for this reaction is going to be little c multiplying delta H per mole formation for C minus little a delta H per mole formation of A minus little b delta H per mole formation of B. And I'll try to work through a few examples illustrating how this works, which hopefully will make both the language and how these are used together a little more familiar and hopefully a little more clear and a little less garbled than my explanation of this section very likely comes across as. So we'll work through examples of this on the following day. That's all for this section, and we'll see you again next day. Thank you very much.